Okay, let's continue thermodynamics. So we were talking about, the properties, any characteristic of a system can be, the pressure, temperature, energy, mass, volume, the parameters that represents a system is called property. And there are four, the main properties that we are going to study in thermodynamics. They are pressure, temperature, volume, and mass. And among them, some are intensive properties and the others are extensive properties. So intensive properties mean those that are independent of mass, such as temperature, pressure. Like, for example, the pressure of a system, pressure of any system in this classroom, like myself or wall or screen or light, anything, they have all different masses, but they share the same pressure and temperature. So pressures and temperatures are considered as independent of mass, so they are intensive properties. On the other hand, volume, mass, momentum, energy, those are extensive properties. They depending on the size, they depending on the mass of the system. So if you increase the mass, its its extensive properties go up. For example, the total energy. If the mass goes up, the total energy goes up. So how can we, determine whether it is intensive properties or extensive properties? The simplest way to determine whether it is one or the other is just divide that property by mass. So if you, or multiply by mass. So if you multiply temperature by mass times temperature, what does it mean? It means nothing in physics. So temperature is independent of mass. What about pressure? Pressure times mass or pressure divided by mass, they don't mean anything in physics. So pressure is independent of mass. But what about, the energy? Energy divided by mass. That is energy per unit mass, right? What is mass divided by volume? Volume divided by mass. They are specific volume, the inverse of density. So it means something in physics. So volume, energy, those are extensive properties. Now there's a problem. If you want to solve any, the governing equations such as conservation of mass principle, conservation of energy principle, conservation of momentum principle, the problem is going to be if you mix extensive properties and intensive properties, some are dependent of mass, the others are not. So, you cannot, they don't work. So in an equation, you want to use only intensive properties or extensive properties. However, some properties are already intensive properties, some are already extensive properties. So how are we going to use both of them in an equation? The simple solution is you can divide extensive properties by mass to look like intensive property, like energy. If you divide the total energy of a system by mass, it becomes the total energy per unit mass. So it's an intensive property. You can use it, you can mix it with other intensive properties such as pressure or temperature. What about volume? Instead of volume, you can divide the volume by mass. Then it becomes specific volume, which is volume per unit mass. So you can use it with other intensive properties. So those extensive properties that are divided by mass are called specific properties. So in a governing equation such as energy balance equation, mass balance equation, or entropy equation, we use either intensive properties or specific properties. Okay? Then how do we know, in mathematics, how do we know one is extensive property or one is intensive property or specific property? If you have like energy, total energy, or total volume. So let's say total energy is E or total volume is V. They are extensive properties. If we divide them by mass, such as total energy divided by mass, it becomes energy per unit mass. In other words, specific energy. This specific energy is lowercase e. What about volume? Volume divided by mass becomes specific volume. So if you use lowercase, if you see a lowercase of an extensive property, you can assume that it's going to be that property per unit mass, which is specific volume, specific energy, specific enthalpy, specific entropy, specific, etc., etc. Okay? So it is important, how you write in an equation, whether it is capital or lowercase. They mean different things. Usually lowercase is the specific capital, right? Specific energy is lowercase e. Specific volume is lowercase v. Or internal energy that you are going to study later. Actual internal energy is U divided by mass. It becomes specific internal energy, lowercase u. What about enthalpy? Capital H divided by mass, it becomes specific enthalpy. What about entropy? S divided by mass, it becomes specific entropy. Okay? Then let's talk about some properties besides thermodynamics. First, one of the most widely used property is density. Density is mass per unit volume. And its unit in SI is going to be kilogram per cubic meters. But in thermodynamics, we use specific volume rather than density. So density is mass per volume, and specific volume is volume per mass. So if this rho is density, then specific volume is going to be rho is going to be 1 over specific volume V, or specific volume V is 1 over density. Then why do we use specific volume rather than density, which is more widely known? Because we use many different specific properties. So it is convenient for us to use a specific volume rather than density. So we can use a specific volume, specific internal energy, specific entropy, specific enthalpy, etc. Okay? We are going to talk about this specific volume later, when we go to chapter 2. What about the other one? Specific gravity. It is the ratio of the density of a substance to the density of some standard substance at a specific temperature. Usually we use water at 4 degrees Celsius, which is the water at the sea is the standard material. And why do we use water at 4 degrees Celsius? Because the density of water at 4 degrees Celsius is very simple to remember. So what is the density value? Density of water is 1,000 kilogram per cubic meters. So it's pretty simple. So because of its simplicity, we use water at 4 degrees Celsius as the reference when we determine specific gravity. These are some specific gravities of widely used materials. The one that we use often in thermodynamics or fluid mechanics is this one, mercury. Its specific gravity is 13.6. That means it is 13.6 times heavier than water. So when we say specific gravity is 13.6. Then what is the density of mercury? Specific gravity of mercury, which is Hg, is 13.6. That means density over density of water is 13.6. What is the density of water? 1,000 kilogram per cubic meters. What is the density of mercury? 13.6 times 1,000, 13,600 kilogram per cubic meters. Because of this high density, we use this mercury often when we measure atmospheric pressure. We are going to talk about that later when we discuss pressure, okay? The last one, besides, the thermodynamic properties are specific weight. Specific weight is density times gravity. Then why do we use this specific weight? There's no, there's no reason in physics, but density times gravity, they come together very often, especially when we talk, they talk about pressure. So we combine them and say specific rate rather than, the using density, gravity alone. Okay. So later, when we talk about pressure change, like for example, if you go up, pressure goes down. If you go down, pressure goes up. We know that, right, from our experience. You remember that, when you go to the swimming pool in the SAC, Student Activity Center, there's a swimming pool. If you dive into the water and then swim underwater, then you feel pressure, right? Higher than outside. So breathing in the water is harder than breathing outside because the pressure by water is higher than pressure outside in air. You also remember when you climbed up Mountain Everest and then it's much density is not that high. You don't remember? I don't remember. We've never been there, right? But the density, on top of Mountain Everest is way, the lower than, the here, and its density, its pressure value is much less. So if we want to determine, how pressure changes, we use this equation. Delta P is rho GH. There you can see density times gravity, so we can say gamma H. What is delta? Delta is difference. Difference in pressure can be determined by specific weight times height. We are going to talk about this later at the end of this chapter 1, and when we, discuss pressure, because there are lots of things that, we need to, go over, okay? So until then, that's everything about this slide, okay? By the way, if you think that, that I'm going too fast or too slow, just let me know, okay? So next one, state and equilibrium. State and equilibrium means that, when we, we assume in thermodynamics, we assume that, our system, when we analyze a system thermodynamically, we assume that everywhere is in thermal equilibrium. So, for example, if you buy this coffee for the first time, at the beginning, whatever the people in McDonald's, pour coffee inside, some temperature on top is going to be maybe higher than the temperature at the bottom, but after 10 to 20 seconds later, everywhere is going to be homogeneously mixed, right? So our assumption when we solve any thermodynamic problem thermodynamically, we assume that everywhere is in thermal equilibrium, which means that temperature is uniform. So if we say it's a cooling process, so heat is removed from the coffee to the surroundings, we assume that initially everywhere in the coffee is going to be 90 degrees Celsius. Maybe 2 minutes later, everywhere in the system is going to be 88. Everywhere in the system is going to be 86. So we assume that, that the temperature, the changes, uniformly. That's our assumption. So, when we say, everywhere is in the same temperature, we assume that it is in thermal equilibrium. Okay. So then how can we solve this kind of problems? By using this. So there's a 32 degrees Celsius, 32 degrees Celsius, 32 degrees Celsius, 32 degrees Celsius. I'm talking about this one. And the surrounding is at 20 degrees Celsius. Then what do we expect? Due to the second law of thermodynamics, we assume that heat transfers from a higher temperature point to a lower temperature point. So the heat transfer direction is this way. So to understand this heat transfer, we need to define system, its surroundings, and its boundary. So in this case, inside this box is going to be system. Outside is going to be its surroundings. And this box is going to be its boundary. So we study energy transfer between a system and its surroundings. So to study that, we need to assume everywhere in the system is in thermal equilibrium. Everywhere outside is going to be in thermal equilibrium. So when I say what is the temperature of the system, it's going to be 32. What is the temperature of the surrounding? It's going to be 20. Then what about this case? Of course, we can assume that initially it was like that, and after a certain time, it can be in thermal equilibrium. What about if by how? By the heat transfer from 42 degrees Celsius to 20 degrees Celsius, or 35 degrees Celsius to 23 degrees Celsius, and after this internal heat transfer, it's going to be all the way 32 degrees Celsius. Then you can do thermodynamic analysis. Then you may have a question. What about if I want to study heat transfer from 42 degrees Celsius to 20 degrees Celsius? Can't we do that thermodynamically? Yes, you can. In that case, we can assume this one is our system, and the outside is going to be its surroundings, and we study heat transfer from the system to the surroundings. So there's nothing that we can solve thermodynamically. It all depends on how you define your problem. So you can decide that in the box, entire the system, entire material in the box is going to be your system. Then you assume that everywhere in the system is in thermal equilibrium. Or if you want to study on a specific, the part of the box, then you can define this is our system. The rest of them is the surrounding. Then you can study energy transfer within the box. So defining the right system and right surroundings, give you, the way to analyze, the every other system. Okay. So one of the key, the thing that in thermodynamics that you need to study is how you design a problem, so that you can, obtain, the whatever you want to, whatever the results that you want to use for your application. Okay. Then processes and cycle. So when you talk about, the heat transfer, let's talk about the simplest, the example. This is a hot coffee, and there's a heat transfer from this coffee to the surrounding air. Okay, that's one of the simplest case. Then we have this coffee, which is hot. This one is red, doesn't make sense. I have a brown. So let's use this brown to represent this coffee. So we have a coffee, and there's a heat transfer from this coffee to the surroundings. And initially, the coffee was at 90 degrees Celsius. Surrounding is at 20 degrees Celsius. Then what do you expect? We expect that, because of this heat transfer, the temperature of the coffee is going to decrease. from 90, 80, 70, 60, and 50. So let's assume that after 10 minutes, the temperature of the coffee went down from 90 to 60. So initially it was 90 degrees Celsius. Due to this heat transfer, it becomes 60 degrees Celsius. So it's a cooling process, right? It's a cooling process. Heat is removed. And in this cooling process, there are two states. The first state is the initial state. The temperature was 90 before this cooling process. And there's another state, which is the final state. The temperature is 60. So whenever there is one process, you should have two states, initial and the final state. Okay? Then what about if you have two processes? How many states do you need? Oh, no, you have a first state, one process, second state, two process, third state. So if you have two processes, you have three states. If you have three processes, you have 1, 2, 3, 4 states. Make sense? Okay. Path is the series of the states through which a system passes during a process. So the name, it's very simple. It means that the way to cool this coffee, there are many different ways. You can just leave it on the table, or you can put this one in a refrigerator. You can use condensing, the coils, and then put it in, and then trying to make it ice. So there are many different ways. Quasi-static and quasi-equilibrium process means that, we assume it goes through this, the figure. We assume that when the temperature of this coffee goes down during a cooling process, we assume that the process occurs slow enough. So you can assume that initially everywhere is 90. After 1 minute, everywhere is 80. After 2 minutes, everywhere is 70. That is quasi-static or quasi-equilibrium process. That is our assumption when we solve a thermodynamic problem. Okay. So among many processes, what we study is how pressure, temperature, and volume change during a process. Okay. So for example, in this cooling process, we know temperature goes down, right? So in this case, temperature goes down. Temperature is going down. So let's say, when temperature goes down, what happened to pressure of this coffee? Goes up or goes down? The answer is, we don't know, because we have no information about its volume, right? Because they are all connected. So when temperature goes up, pressure can go up or down depending on how volume changes. So we cannot say how this pressure changes because of this temperature change. So to understand this phenomenon easily, what we do is we make one property constant and look at the other two. So in this case, we can assume that pressure is constant and look at the volume. So if we say pressure is constant and temperature goes down, what happened to its volume? Volume goes down. When temperature goes up, volume goes up. If it is not easy to accept, then think about a good example. About the 2 or 3 weeks ago, there was a balloon festival in Midland. So you know what it is, right? People goes in and then go fly. How they go up? So use a remote controller and then No, usually they heat, right? So they have a burner here, and what it does, it increases the temperature of the air inside, right? What happens to the air when temperature goes up? Assuming pressure remains constant, its volume goes up, meaning it's that its density goes down. The air inside becomes lighter. That's how this one moves upward, right? So when temperature goes up, as long as pressure remains constant, volume goes up, which means that density goes down. If you want to change pressure while we are going up, you need to go very, very high. The pressure change in the air is way less than pressure change in, let's say, where. You can think about this way. If you go to the swimming pool and then dive into the swimming pool, let the depth of the swimming pool in the sag is pretty, not that deep, right? But imagine the swimming pool that when you watch Olympic Games, there's a diving, right? So usually, the swimming pool for diving, they are pretty deep, right? So when you go in that deep, you get a lot of pressure, right? So let's say that the swimming pool is about the same size as, the 4-floor building. So if you go, maybe 10 meters or 20 meters downward, then the pressure increase is going to be very significant, right? But imagine that you go to the 4th floor in the library. Pressure goes down that much, so you cannot breathe. You need an oxygen tank to go to the 4th floor. What about the Sears Center? It's not the Sears Center anymore, right? In Chicago, there's 100 floors. So if you go to the 100 floors, you need to have check in the lobby, and then they give you oxygen tanks. Then you put it up and then go to the 100th floor. No, we don't. The reason is the pressure change in the air is way, way less than the pressure change in water. So technically, you're right. When you go up, pressure goes down, but very slowly, unless you use unless you the jump from here on top of Mountain Everest, then there is a significant pressure changes. But imagine like a Denver, Colorado. It's like the 2,000 meters on top of mountains. So it is like the multiple the Sears centers, right? But what is the atmospheric pressure there? Only 80% of Mount Pleasant. So the pressure change is that small. But can you dive maybe 20 meters from the surface? It's not easy. If you go, let's say, the 100 meters, if you're not a professional diver, you get, the sick because your lung cannot withstand those, the pressure differences. That's what, the people call, I don't remember, there's a disease, for, the divers, right? They need to go to high pressure oxygen tank to, remove all the, the problems in the lung. I don't remember. I'm not a, what? Right. So nitrogen build up, due to high pressure. So when you go in water, the pressure changes is very significant, but when you are out there in the air, the pressure change is small. But we will talk about that later when we discuss pressure. Okay, we have one section at the end of this chapter 1. It's pretty interesting. Okay, so in this example, we assume that pressure remains constant, and we can understand how temperature, volume are related. Let's look at another example. From another class. Can use it. Now, pressure and temperature and volume. This time, instead of pressure, we can, fix this temperature. We assume that constant temperature. When you have a constant temperature, when pressure goes up, what happens to the volume? We can answer that. What? Come here. Yeah, it goes down. We can say, simply, understand this phenomenon by an example. Let's assume that this is a water bottle. It's not a water bottle. Let's assume that it's a water bottle. If you squeeze it, then its volume goes down, but the temperature of the water is remain constant, right? Technically, it goes up slightly, but practically in engineering, we assume that it's constant, practically. So when you squeeze it, when you increase pressure, its volume goes down. That means if pressure goes down, volume goes up. So we can understand easily when you make one property constant. Let's look at another example. Now, pressure, temperature, and volume. This time I'm going to say volume is constant. When pressure goes up, what happens to the temperature? Yeah, it goes up. When the pressure goes down, temperature goes down. So we can understand easily when we fix one property. So in thermodynamics, there are many, many different processes, but we focus on these three simple cases. They are isothermal process when temperature is constant, isobaric process when pressure is constant, and isochoric process when volume is constant. And a cycle means you have a multiple processes. So initial state, state number 2, state number 3, state number 4. After our multiple processes and the final state is the same as initial state, we say it's a cycle. Okay? Of course, when we go to chapter 3 and 4, we are going to solve many, the constant temperature processes, constant pressure processes, constant volume processes. We will understand how to, to solve them. Right now, I'm just introducing there are, the such processes are available, okay? So don't worry if you're not 100%, sure about, what we do here. This is just, the introductory level, and when we go to, the actual thermodynamics, we will solve problems related to each of them, okay? Then another important thing is going to be steady and unsteady. Unsteady is also called as transient. So when you hear transient process, unsteady process, you can assume that they are about the same thing, okay? Steady and unsteady. What it means, a steady process, what it makes an unsteady process. The simple answer is time. When it is time independent, it's a steady process. When it is time dependent, it is unsteady process. Then the question is, how do I know whether it is time dependent or time independent? The answer is simple. When you look at a thermodynamics problem, there is a main property. If the property changes in time, that's a time-dependent problem. If the property does not change in time, it's a time-independent problem. So let's go back to this coffee again. So initially 90 degrees Celsius, after it's a cooling process, after 1 hour, it becomes 60 degrees Celsius. So what is the main property in this example? The temperature of our system, the temperature of the coffee. So what happened to the temperature? After 1 hour, initially it was 90 degrees Celsius, and it became 60 degrees Celsius after the cooling process. So the property has been changed in time. So it is unsteady process. Okay? What about this cell phone? I'm recording this lecture so you can review them, when you are, studying this, afterward. The temperature of this cell phone does not change in time, does it? So right now it's about 20 degrees Celsius, so I don't feel any heat. But later tonight it becomes, a fireball and the burning itself out. No, there's no such a thing. Or it becomes, the ice, so I can put it in my coffee and make a iced coffee. No, the temperature remains constant. So the cell phone is going to be considered as steady process when we only talk about its temperature. Okay? Then let's talk about, the real life example. Let's talk about an engineering device that we use often. Let's assume that, that you came to the, the school, by driving. Okay. So when you, to get into your car, what do you see? What do you see in front of you? Windshield, great view in Mount Pleasant. Yeah, right. But, we usually want to check these things. There are 1, 2, 3, and 4 gauges. Unless you have a, fancy, expensive luxury cars, they don't usually have them. They have numbers, right? Mine has it like this. So when the left-hand side, it says MPH. No, it's RPM. Right-hand side is MPH. And here EMF and CMH, right? No? It's your first time to see a car. So what is the most important gauges here? Okay. So let's review one by one. So we are going to, consider what the risk factor. So NPH first. How much risk does it have if you don't watch that? Yeah, you get a ticket. So the maximum, unless you know that you can drive like a 300 miles per hour, that's not possible, right? Mine cannot drive that fast. So usually I can say, unless I have a previous record, I will get maybe $100, the ticket for speeding. So you get pulled over if you don't watch that. So the maximum risk is gonna be $100. It's not that big deal, right? What about this one? Oh, if it goes up, if you don't watch that, if you don't change your gears on time, let's assume then you have a manual transmission. Then the worst thing can happen is gonna be, your fuel efficiency goes down. So you consume more fuels. That's not that bad. What about ENF? Oh, this is the only time you like this letter F, right? No? Or should I change that AF? Then you prefer, that this gauge goes this way? No. So the risk factor is gonna be, if it goes to E, that means that you have to, to go to a gas station, you're going to pay about $50 or $60, right? So that's not a big deal. Do you watch this one? Usually, I don't. But what is the risk factor? So while you're driving, one day, I accidentally saw this one and it was pointing H. Then how much risk is gonna be? Oh, that you need to be excited because you're going to buy a new car, right? So what happened is that usually at the beginning it was the pointing C because the engine had been run. So when you start the engine and while driving, we call it warming up, right? So in the warming up, the temperature goes up. This is unsteady process. Once you reach a certain temperature, it stays there. Now it is steady process. So when you're driving, it's not just unsteady or steady. At the beginning, it's a steady process and it becomes unsteady process. I'm sorry. At the beginning, it's an unsteady process. It becomes steady process. And you don't want to see it goes to unsteady again, right? When you see that, you need to be excited because you're going to buy a new car, right? So when you determine whether it is steady or unsteady, what you need to look at? The property of the system. What is the main property of this gauge? The coolant temperature. When the coolant temperature is not changing, then you can assume that it's a steady process. When it is changing, then you can assume that it's an unsteady process. So which one we are going to study in thermodynamics? Both of them. We are going to study unsteady process first in chapter 3, and then we are going to study steady process later in chapter 4. To be more specific, in chapter 3, we are going to study unsteady closed system. In chapter 4, we are going to study steady open system. Closed system. open system. So now we understand, the what steady and unsteady means. If your, the property of interest changes in time, that means unsteady process, it doesn't change in time, steady process, then what it means, the closed and open system. When there is a mass change in your system, it's an open system. When there is no mass change, it's a closed system. So if I talk about this, the coffee, if I open the lid, is it a closed system or an open system? It's a cooling process. Unless you pour, it's closed. Okay? So it doesn't matter, the lid is open or not. What it makes, the closed system or open system is the change of the mass of the system. So unless you pour it down or drink, if the mass of the coffee does not change, you need to neglect the evaporation, okay? Unless there is a mass change, it's a closed system. If there's a mass change, it's an open system, okay? So the main chapters in this thermodynamics are going to be chapter 3 and 4. The next one is, by the way, let me know if I'm going too fast or too slow, okay? The last one is Zeroth law of thermodynamics. It's very simple. Even my, the 4-year-old son can understand that, so just read it. So that's everything except temperature and pressure. Any question before we discuss temperature and pressure? No? Okay. As I told you, in the first class, the last Tuesday, the chapter 1 and chapter 2 are not very fun, so you got to be patient, okay? So if you are not bored until now, you are already addicted to thermodynamics, I can say. All right, temperature first. Ice point and steam point. This is the last time you're going to say ice point or steam point. Once you study thermodynamics, you are going to call them a different name. That is saturation point. That we will talk about that later when we go to chapter 3. So if you meet another mechanical engineer, keep saying steam point, ice point, he didn't do very well in thermodynamics. Okay, ice point means, the temperature, when, the phase changes between solid and liquid. And steam point is between the phase change temperature between liquid and vapor. Then what is ice point? In Celsius, 0 degrees Celsius. And what is steam point? In Celsius, 100 degrees Celsius. So if you ask another engineer, what is ice point of water? And he says, 0 degrees Celsius. Is that right or not? Based on what you see there. Sounds right? But when I ask this question, it sounds like it is no, right? So the answer is no. The reason is that you have to say the ice point of water at 1 atmospheric pressure is 0 degrees Celsius. The steam point of water at 1 atmospheric pressure is 100 degrees Celsius, because as you remember, from this pressure, temperature, volume, they are all connected. When temperature changes, temperature changes. When atmospheric pressure changes, your steam point, ice point will change. I think I told you about the story about restaurants in Denver, didn't I? Okay, so when you go to Denver, nobody is from Denver, Colorado, right? No, okay. So if you go to Denver, Colorado, the city is on top of mountains, so the atmospheric pressure is way less than here. about, here, if it is, about 100 kilopascal in Mount Pleasant or anywhere near the sea level, if you go to Denver, Colorado, the atmospheric pressure is going to be only 80 kilopascal or something. So their steam point there is not 100 degrees Celsius. It's going to be 96, 95, or 94 degrees Celsius. So the temperature of the boiling goes down. What about on top of Mount Everest? Can you cook noodle? Or you can cook noodle. Can you cook delicious noodle? Well, it's pretty subjective, so I cannot say. But usually the steam point on top of Mount Everest is about 60 degrees Celsius. In Fahrenheit, about 140 degrees Fahrenheit. So you see, bubble is forming, but it's not that hot. So when you cook it, let's say, if you cook noodle, I forgot what I was saying. So if you cook noodle, let's say that, to fully cook, that you need to put the noodle in a boiling water for 10 minutes. If you do the same on top of Mount Everest, it's going to be undercooked because the less amount of heat goes in. The same thing goes to Denver, Colorado. Even though the boiling point is not much difference, but their boiling point at their atmospheric pressure is about 94, 95 degrees Celsius. So if you cook noodle for 10 minutes, it's going to be undercooked. So if you use the same recipe in the different atmospheric pressure, the food is not going to be as tasty or as expected. Right? I often to go to Denver, Colorado many times, to work for conferences. I've never seen a single restaurant which is delicious. And I think the reason is they don't hire mechanical engineers in their restaurants. They need to hire mechanical engineers and understand how this temperature changes due to their low atmospheric pressure. I think I went too far, right? So the ice point of water at 1 atmospheric pressure, so you need to say 1 atmospheric pressure, is 0 degrees Celsius and 100 degrees Celsius. In Fahrenheit, 32 Fahrenheit and 212 Fahrenheit. Then how you convert between these two? Or you can ask ChatGPT, but as an engineer studying thermodynamics, you have to know how to do that. It's pretty simple. Ice point is here and steam point is here. In degrees Celsius, ice point is 0, steam point is 100. In Fahrenheit, the ice point is 32 and steam point is 212. So what is the difference between ice point and steam point in degrees Celsius? Is delta T, difference in temperature is 100. In degree Fahrenheit, delta T, the difference in temperature is 180. So the ratio between Celsius and Fahrenheit is going to be 100 to 180. 100 to 180. Let me write it here. Oh, that is 9/5. So let me write this one here. 9/5 is the ratio between the change in degree Celsius and the change in degree Fahrenheit. So if you want to convert from, it's flying, okay. If you want to convert degree Celsius to degree Fahrenheit, you need to multiply by 9/5, then you get degree Fahrenheit. But that's not the end. The starting point is not the same, so you have to add this on top of it. So add 32. Then that's how you convert between degree Celsius and Fahrenheit. Which one is the standard SI unit? The answer is none of them. The standard SI unit is Kelvin. So let's talk about this Kelvin now. But before that, what is the standard English unit? The answer is, again, none of them. The standard English unit is Rankine. Have you heard about that? No, okay. So let's talk about this, the standard units. Then, what is Kelvin? Is Kelvin can be found, determining Kelvin is pretty easy. Degrees Celsius plus 273.15 becomes Kelvin. Or some people say 273.16 in for us. We can just neglect these small numbers. So if you add 273, that should be enough. Practically correct, okay? Because those small differences cannot affect the result. So if you add 273, it becomes Kelvin. Then the question is going to be, oh, I think, the degree Celsius has a very good, the scientific background because, it's based on 0 for ice point, 100 for steam point. Why don't we use this Celsius for standard SI unit? Why do we come up with, another unit, which is Kelvin? Because Kelvin also has a very important, the meaning in physics. What is it? So when we say 20 degrees Celsius, like the room temperature in this classroom, in Kelvin, it's going to be 293 Kelvin. So the temperature in this classroom is approximately 297 Kelvin. Then what about, if the temperature is minus 100 degrees Celsius? Then in Kelvin, it's going to be 173 Kelvin. Then what about minus 273 degrees Celsius? Then it's 0 Kelvin. What is 0 Kelvin? So the importance of this Kelvin is going to be this number. That is called absolute zero. At 0 Kelvin, we assume that there is no thermal energy in a system. So this coffee has a temperature. It's not 90 degrees Celsius anymore. I bought it 2 hours ago, so it's not that the hot, but it has a temperature. Let's say 40 degrees Celsius. That means that it has heat, right? So if you remove heat, temperature goes down, right? If you remove heat, temperature goes down. But there's a limited amount of heat left over, right? So if you remove all the remaining heat, there's no more heat left over. What is the temperature? Minus 2000? No, that is 0 Kelvin. So 0 Kelvin is the lowest possible temperature you can reach. So there's no minus 10 Kelvin, minus 5 Kelvin, because there's no more heat you can remove. So when you remove any thermal energy from a system, this is the temperature you can reach. So this is the lowest possible temperature. So if you watch, any science movie and saying that, in space, there's no sunlight, so the temperature is minus 500 degrees Celsius. Is it possible? No, that's not possible, because the lowest possible temperature is this one. Okay. So that is Kelvin. So sounds like it has a very good, meaning in, the physics. So we use this as a standard SI unit. Then what is this Rankine? That's the same thing. When 0 Rankine means that the absolute zero. So that's everything about temperature. Any question? No? Now, let's talk about pressure. I guess, I usually, you have you're less familiar, with the pressure than temperature. So I guess, that we need, to spend more time to discuss pressure, okay? So let's talk about unit first. And let's talk about what is pressure. Pressure is a force by fluid. But when we talk about, the force, we imagine something like that. If I punch this, the whiteboard, I just gave force on this point, right? Because I have my, the fist, where the, the fist is, the touching, that's where force is acting on, right? But what about fluid? The air in this classroom. Air has pressure. Air, the provide force. So air force by air is acting on this whiteboard. But where? Here? 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 No, everywhere. Why everywhere? Because air is a fluid. What is the definition of a fluid? The material that continuously deforms. So what is the shape of air? Well, there's no shape. It depends on its container. So if you pour coffee into this cup, the shape of coffee is going to be exactly this cup. If you pour this coffee into this cleaner, then the shape of the coffee is going to be exactly this one because it has no shape. It continuously deforms. So air cannot provide force on this point. Air can provide force everywhere. Okay? So since we cannot determine the point where force is acting on by fluid, we just divide force by air by the entire area, where the force is acting on. That is pressure. So pressure is force divided by area. Then what is the SI unit of force? Newton. Then what is the area? Meter square. So pressure is going to be Newton per meter square. That is Pascal. Then 1 Pascal. Then the next question you may have is, how big is it? Is it big or small? Of course, the answer is going to be pretty subjective, right? But usually 1 Pascal is extremely small number. Imagine the pressure by atmosphere. So you are experiencing pressure by air in this classroom, but you don't feel that, right? Because you have the air in your body that give you the same pressure to outside. So if this is your body, I'm not measuring, the painting, so it looks like a human, right? So there's a air pressure acting on your body, and there's a same amount of pressure from the air inside your lung or your body. So this is the pressure from your body. This is the pressure from the atmosphere. Which one is greater than the other? None of them. They should be the same. If the pressure by your body is greater than the atmosphere, then what's going to happen is that your body becomes bigger and bigger. What about if the pressure by outside, the atmosphere pressure, is greater than the body pressure? It goes down like that. Okay. So when you see the inner face does not move, then you can say there's a pressure equilibrium. The net force is 0. Okay. Then what is this atmospheric pressure in Pascal? Atmospheric pressure P ATM. It's not automatic teller machine. Okay, not the device that give you free money. It's not free. It's coming from your account, right? It's a pressure, atmospheric pressure. So atmospheric pressure in Pascal is going to be 101,325 Pascal. So now you can see 1 Pascal is pretty small, right? So in thermodynamics, we usually use kilopascal. 1 kilopascal is 1,000 Pascal. And this one, atmosphere pressure is going to be 101.325 kilopascal, approximately 100 kilopascal, right? Now, it looks like a reasonable number we can use in our equation, right? So we use kilopascal in thermodynamics. Another unit is, by the way, SI unit. The standard SI unit for pressure is Pascal. And there's another unit, ATM. 1 ATM is 101.325 kilopascal. So you may see ATM also. Another, the pressure unit is bar, not the bar that we can drink. This is unit of, the pressure. 1 bar is 100 kilopascal. And there's also more units, they're like millimeter, HG, or inch, HG. Those things are pretty common when you talk about weather. We will talk about that later. So these are the common units in pressure. Okay. Then which one we are going to use? Sometimes we use ATM, sometimes we use kilopascal, sometimes we use bar. So some, the property tables are in bar, some property tables are in kilopascal, megapascal, some properties in a property table is in ATM. So you have to, get used to all of them, not just one. Okay. So that is the information here. Okay, this one. Then we have absolute pressure, gauge pressure, and vacuum pressure. So pressure looks a little more complicated in temperature, right? So then what does it mean when we prepare for our first exam? So the first exam covers chapter 1, 2, 3, right? So that means that I need to give you at least one problem from chapter 1. So among all the areas that we covered from yesterday, which area do you think that I'm going to give you a problem? This one, this one, this one. So that motivates you a little bit, right? Okay. So let's talk about absolute pressure, gauge pressure, vacuum pressure. If you go to the other side of the building, there are machine shops, metal shops, and the many shops over there, right? Sometimes you see, even outside the building, you see a gas tank, right? Something like that. And usually there's a gauge, looks like that, pointing something. So let's say when this one reads 200 kilopascal, when outside, the atmospheric pressure, PATM is 100 kilopascal. When you see 200 kilopascal, is this the pressure of the whatever the gas in the chamber? Of course, I haven't discussed that. You don't know, but let's guess. If I say, that the gas pressure inside is going to be 200, is it right or wrong? You have a 50% chance to be right. Yes or wrong, right? So the answer is no. The pressure of the gas is not this number. Then what is it? It's a gauge pressure. This gauge can only, tell you the difference between the pressure inside the gas and atmospheric pressure. That is called gauge pressure. So when it starts 200 kilopascal, that is the difference between gas pressure and outside atmospheric pressure. So what is the absolute pressure? ABS. ABS. P anti-braking system. No, that's not. This absolute pressure. So the absolute pressure is going to be 300 kilopascal. Then gauge pressure can only measure the difference between absolute pressure and outside atmospheric pressure. So P gauge is going to be 200 and atmospheric pressure is 100. That's the physics. And let's talk about mathematics. PABS is P gauge plus PATM. So gauge pressure plus, the atmospheric pressure is called absolute pressure. Then why don't we just measure absolute pressure, right away? Oh, unfortunately, we cannot do that. If you want to measure absolute pressure, you need to have a pressure measuring device. that measures gauge pressure. You need to have another pressure measuring devices that measures, the atmospheric pressure. This one is called, the one measures gauge pressure is called manometer. The one measures the atmospheric pressure is called barometer. So we are going to talk about, how we measure manometer and barometer later, okay? So if you, put all the numbers, let's say 300 is 200 plus 100, makes sense mathematically. No problem. So that's the end of, the explanation, introduction. No, there's another one, vacuum pressure. So what does it mean? What about if the gas in the cylinder is vacuum? When I say it is on the vacuum, that doesn't mean that there is no gas inside. That means the pressure inside the cylinder is less than atmospheric pressure. So if it is high vacuum, we have a less amount of air gas inside. Low vacuum means the more, the gas in the chamber, but the absolute pressure should be less than outside. So if it is under vacuum, let's say that atmospheric pressure is, absolute pressure is only 20 kilopascal, while outside is 100 kilopascal. Then let's see if we can use this one. Absolute pressure is 20, atmospheric pressure is 100, so the gauge pressure should be what? Minus 80. And the pressure value becomes positive and negative? No. Pressure cannot be a negative value. So we cannot use this equation anymore. Then what we can do? We can say PATM is PABS plus P gauge. Then it makes sense. Look at that. 20, 80, and 100. So mathematically correct, right? However, if you say this gauge, which is different equation than this one, then you get confused between this gauge pressure, this gauge pressure. So let's use another name, that is vacuum pressure. So vacuum pressure and gauge pressure, they all means the difference between atmospheric pressure and absolute pressure. But when the absolute pressure greater than atmospheric pressure, that is gauge pressure. When absolute pressure is less than the atmospheric pressure, that is vacuum pressure. Okay. So one thing that you need to remember is that either gauge pressure or vacuum pressure, they all mean the difference between absolute pressure and gauge pressure. Absolute pressure and atmospheric pressure. We have 3 more minutes. Any question up to here? So we studied the units of pressure, Pascal, ATM, bar, millimeter, Hg, and we studied what are absolute pressures, gauge pressures, and atmospheric pressure. So the remaining 3 minutes, we can talk about how pressure changes. Changing pressure is pretty simple to calculate. The rule is always number one, just one. Delta P is rho GH, or you can say gamma H, the specific weight. Delta P is rho GH. What is rho? Density. What is G? Gravity. H? Height. Then you can calculate the difference in pressure. And the change in pressure, what makes the change of pressure? Gravity. So if you go up the opposite direction of the gravity, pressure goes down. If you go down in the same direction as the gravity, the pressure goes up. Then what about if you go horizontally? Pressure does not change. So pressure here and pressure in my home country, South Korea, not the same. But pressure here and the pressure in Denver, Colorado, same. Because the altitude of Denver, Colorado is much higher. The pressure in Mount Pleasant is even higher. Now, if you look at this equation, the most important property is going to be this one, density. So, depending on the density, the change of pressure matters. So, what is the density of air? We don't know usually, so let me give you, the just reference value. At the sea level, about this room is about approximately 1.2 kilogram per cubic meters. What about the density value on top of Mountain Everest? 0 point something, much less, because we have less amount of air. Then what is the density value? We have 1 minute, just 1 minute. What is the density of water? 1,000 kilogram per cubic meters. So, for simplicity, let's assume that the pressure of air is approximately 1, which is fine, because when you go up, density goes down. The average we can say about 1. The change in pressure in water is 1,000 times greater than the change in air. So if you dive into the swimming pool 1 meter, that is the same pressure change if you go 1,000 meters above. So how high is Mountain Everest? 8,843 when I was born. Now 8,845 now, because there's a change depending on the amount of snow. So that is approximately the same as the 10 meters, 8 meters in the water. That much difference. Let me give you another example. 1 more minute. Let me give you another example. Let's assume that have you been to the swimming pool in the sack? There are rooms inside. What are those rooms? Restrooms? No, sauna, right? When you go into the sauna, what is the temperature inside? Yeah, right. How? Usually, I don't know about this one, but if you go to the commercial, the sauna, their temperatures are above the boiling temperature of water. Can you survive? Even though it is hotter than boiling temperature of water, you can survive. Now, let's assume that that you are going to, just for fun, to boil the water in the swimming pool. So it's boiling. Can you jump in? You can. Once in a lifetime, right? You cannot survive. Why is that? Even though you can survive in a dry sauna at higher temperature than boiling water, but you cannot survive in water because of the density difference. Air density is way, way less. So the amount of heat transfer from the hot air to your skin is 1,000 times less than the rate of heat transfer from the water. Roughly. Of course, if you go deeper, it's more complicated. But usually, the rate of heat transfer in water is way higher, so you cannot survive. But you can survive in dry sauna. The same thing goes here. The density is the key factor, the affecting pressure change. Okay, that's all. We will continue discuss this pressure later on Tuesday.